triple integral examples today. We're going to continue on with this tetrahedron problem. So the tetrahedron, we decided, the first thing we did was we found the four planes. And I'm coming through loud and clear. Everyone can hear me?
Yep.
Awesome. All right. So this tetrahedron, we said that plane number one, I don't know if this is exactly the order, but plane number one was x equals 0. And then plane number two was y equals 0. So there's the x equals 0 is like the back, y equals 0 is like the left side. And then this kind of bottom-ish plane here, we call that, figured out that was z was 1/2 x, or x is 2z, so those are one and the same. There's two different ways to write that. And then we went through the process of finding this oblique plane, this plane that kind of on an angle to the axes and the coordinate planes. We found the parallel vectors in the plane. We took the cross product to get the orthogonal vector. We plugged the orthogonal vector and a point into the equation of the plane. And then we got three versions of it. We solved for z, we solved for y, and we solved for x. So all of these are the same plane, and we called that plane number 4. And so those are our 4 planes. And we did some examples of, we did the type A example. Type A is dz first. And so we said, basically we said with our triple integrals, there's the first inside integral, which is surface to surface, right? And then the outside double integral was the next part, and that's how the solid projects into the plane of the other two variables. And so then we said the next part was an outside double integral, and just like the double integrals we worked on for a week, right? So absolutely the same. The only thing is we got to get the right projection of that solid into the plane. Okay? So this was our overall approach to these. So I think we did, what did we do? We did a type A, where it was bottom to top surface first. Then we did a type C, which was a left to right surface first. So now we're going to do a type B. Let's do type B1. So B1 would be dx first. And then type 1 is what? Bottom to top, left to right. So dx, dz, dy. So if we're doing dx first, we're going from what surface to what surface to start with. So in terms of top, back, left, right, front, this goes from what to what, dx?
Left to right.
He wants left to right. Agree with that? So x, remember our x-axis is this one here.
It'll be back to front.
Yeah, so it's going to be back to front, right? So it's going to be like...
My bad.
Oh, you're right. That's okay. It'd be left to right in R2, but remember in R3, the x-axis comes out at us. So we're going to fire arrows from behind into this thing, and we're asking where do the arrows pierce into the solid? In the back. That'll be the back surface. And then where do the arrows kind of emerge and exit the surface in the front? Okay, so where do they enter this? So we got 4 surfaces here. So which surface is the back where the arrows enter in?
Surface 4.
4 is the back. Agree with that? 4 was this plane here, right? This like the plane that was like slanted to all the other planes. Is that the back of it?
Should be surface 2.
Y equals 0.
Surface 1.
Surface
sorry.
1. X equals 0, right? So the back of this is the YZ plane, right? It's this triangle back here. That's X equals 0. So our back is 0. And then what about the front? What's the front of this thing? Where do the arrows come out?
Could you turn the surface?
That's what I'm trying to do, yeah. So where's the front of the solid?
Surface. That's going to be the surface 4 and surface 3.
Definitely 4, but do you notice that it's also 3? For arrows that are down there by the y-axis, so arrows down here, they're not going to exit surface 4, they're going to exit surface 3. Does everyone see that in the front? So this is part of the front. It's just kind of a sliver down there, it's not too big, but any arrows coming in the back near the y-axis down here at the bottom are going to exit through this surface, not this one. So what does that mean? If our back is all 0, but our front is split up between two surfaces, that means we have to do what?
Split it into 2 intervals.
Yeah, and so with our experience with double integrals, this isn't that bad, right? So because we know the strategy here, we know what's up. So don't try to do that. So we just know that when we so it's dx, dz, dy. So the back is always 0, and the front, sometimes the front for higher z values, the front is this, and so we need it as a x as a function, right? So we're going to choose this version of our plane. I'll do it here. Okay, so sometimes the front is that, and then sometimes the front is this. What are we going to use for the upper limit of integration for that then? Right here.
2z.
Yeah, x equals 2z. All right, and just like with our double integrals, so the outside double integral is going to associate with the part of the region such that this was the exiting plane, right? So we're gonna project our solid into the YZ plane, and the part of the projection that is this plane will determine the double integral for that exiting plane. And then when we exit out 2z, that region right there will determine this double integral. Okay, so let's do this one first. So we're going to do dz dy. So what we need to do then is we need to define these boundaries in this projecting region, right? So this is how the solid projects into the YZ plane. So this is a point, I think 3 here, and this is 4 here, and 0, and this was 1. Based on work we did before, we knew this was the point 2, 0, 1. This was 0, 0, 4, and this is 0, 3, 0. And so based on that, we can write these lines. So this is z equals 4, z-intercept. And then rise over run, so you got -4 over 3. So that's that line there. And then this line here is intercept. Rise over run here is -1 over 3. So I've got this line is z equals 4 minus 4/3 y. This one is 1 minus 1/3 y, based on these points here. And so when we come out the front at this plane, we're going to go what? Bottom to top, left to right. So what's the bottom? Z equals, what's the bottom? Exiting out this plane?
0.
Nope, exiting out. So this upper integral up here is for our front exit of this part here.
So would it be 1 minus 1/3 y?
Yeah, so the bottom is 1 minus 1/3 y. And the top is the 4 minus 4/3 y. And then from left to right. So we know we've got all these strips from bottom to top, and the first strip on the left is at y equals
0.
and the last strip on the right is at y equals
3.
3. Okay, plus, adding these together. Then when we exit out 2z, that's this plane here, so we're exiting out 2z. And so we need the double integral for that region where we exit out 2z. So bottom to top, bottom is
0.
that's 0. Top is
1 minus 1/3 y.
yeah. So it makes sense. The top of this part is the bottom of this part up here. So it's going to be top here, bottom here, and then again from 0 to 3. Questions on that double integral? So we need to split it up because our front surface was split up. Sometimes it's that, sometimes it's that. Any questions on that one?
How we get 2z again?
2z. So that was plane 3 was z equals 1/2 x, which is the same as x equals 2z. But we need the x version because it's dx. So back to front is going to be x equals something and x equals something. So that's this plane under here written as x equals a function of y and z. Does it make sense?
Yes, yes.
Okay, cool. Other questions?
X equals -8 minus y minus 2/3 c plus 8/3 is the back plane, right?
No, that's the more complicated one. The one that kind of sits on the top and the front. The back plane is 0.
Okay, yeah.
The back plane is 0. This is the 3 versions of this complicated oblique plane. That serves as, it actually serves as the top, the left, and the front. So that's why we need the 3 different versions of it, depending on what variable we're working in.
Yeah, thank you.
Sure. Okay, let's, I want to go on and do a different example now. Any more questions about the tetrahedron? All right, let's go and look at this one. So we really got into our surfaces. So that's, in fact, the whole rest of the course, lots of these problems are going to be dealing with these basic surfaces. That's why we had them on exam 1 and exam 2. So we got paraboloids, double cones, all kinds of cylinders, spheres, ellipsoids, planes. I think that was our main list. So you got to recognize them by the equation, be able to make just at least general sketches. And now we got to make sketches of multiple ones to form a solid. So let's see how this goes. So what is z equals y squared? Z equals y squared is what?
Parabolic cylinder.
Okay, it's a cylinder because x is missing, right? When one of the variables of the 3 is missing, that's like a curve extended in the direction of the missing variable, which makes a cylinder. And this is based on a parabola, so parabolic cylinder. Okay, and then what about this one? This one's a parabola. It's just a curve. Is that right?
Would this also be a cylinder?
Yeah, so
In the z direction?
so all right, so at some point we got to get to this, and we tested this on both tests. If you have an equation of just two variables, we're in R3, it's not a curve. It's a cylinder. It's based on a curve, but it extends in the direction of the missing variable to form a surface, a cylinder. Got to get this. And so lots of you are still seeing these equations of two variables and you're saying they're curves. It's very common, but at some point it's got to click for everybody. Equations of two variables in R3 are cylinders. They're surfaces. Okay? All right, so we're going to try to, and then also for this solid, we also got x equals 0 and z equals 0. All right, so z equals 0 is the xy plane. X equals 0 is, this, like the plane of your screen. So z equals y squared. Z equals y squared. What is that? So we can start by drawing the curve and then extend it in the x direction. Okay, like this. Something like that. And then we're going to extend it in the x. Okay, so this is like that. And then this parabolic cylinder, 4 minus x squared. So I'm going to draw that separately so we can kind of try to figure out what this looks like. So 4 minus x squared has a y-intercept of 4 and opens downward in the y direction like this. Intersects, has an intercept up there of 4, 2, -2. So that, you have to kind of twist that and change it because we know our x is here and our y is here. So that would be like here. And so we imagine, actually we don't need the back of it there because we know we're going to be in the first octant. So we maybe just draw this part of it. And then what? And then that's going to extend up, right? So can we see what's happening here? We've got, so that's a vertical surface. This one is more, it's not horizontal, but it's going to be more like the top of it, right? This is going to be like the lateral side surface. This is going to be the top. And so we know that x equals 0 is the back, so we're going to have like, this is going to be the back of it right here. Okay, and then the bottom is going to be, that's going to be an edge on the bottom. And then it's going to, from here, you got to imagine cutting, what? So cutting down, like this is a knife cutting down on this. It's going to make a cut like this on, this is z equals y squared. Imagine cutting downward with this cylinder onto z equals y squared, and you're going to get an edge like this. And so now it's starting to take form here. So it's that kind of wedge, curved wedge thing back there. So let's erase some things we don't need here. Okay, do you see it? Does it make sense? So this is this surface here, this vertical lateral surface is the y equals 4 minus x squared. This kind of top to this thing is z equals y squared. So let's just write some coordinates down here. This would be 0, 4, 0. This would be 0, 4, 16. this would be 2, 0, 0. Okay, can you see it? Does it make sense? So we get z equals y squared, 4 minus x squared. The bottom is equals 0. The back is x equals 0. So let's, we started doing some splitting it up. So let's do a kind of straightforward one here. How about type A1? Type A is where we do dz first. And then 1 is, we know our dy dx. So we go from, start with what surface to what surface? If we do dz first, 0. Bottom to top. dz first means bottom surface to top surface. What's the bottom surface? Z equals?
0.
0. Top surface, z equals?
Y squared.
Is it split up or is it all y squared?
All y squared. All y squared.
Yeah, all y squared. This lateral surface is vertical. So the arrows are parallel to that, right? The arrows cannot pierce out of that if they're shooting straight up. This is like a wall. It's like a sidewall. So yeah, the whole surface, the whole top surface is y squared. All right, now we're going to project into which plane?
Y.
To do the double integral, we're projecting into which plane?
XY plane.
XY plane, right? So we're going to project in the XY plane. And looking at that, we're up here at 4, y equals 4, x equals 2. And then we got that parabola. And then we got these edges on the axes. So there's our region, and we're going to go bottom to top. So here we go. Bottom to top, y equals 0, 2.
4 minus x squared.
Good. 4 minus x squared. Y equals 0 to y equals 4 minus x squared. And then the first one of those is at the left at x equals 0, 2.
X equals 2.
0 to 2. Straightforward one there. Okay, let's do B again.
Professor, I just have a question.
Sure.
How do you know which plane you'd want to project the solid to?
If we go bottom to top, then what's left is y and x, right?
Yeah.
So that's how you know. It's the plane of the remaining two variables.
Okay, awesome. Thank you.
Sure.
How did you pick the order of the integration, like the dz, dy, dx?
I just picked it. Like I said,
Just
I said,
sense.
here's the given problem. That's what I said. Like, here's the given problem. So, does that make sense?
Okay.
There's nothing about the setup. There's nothing about the setup that inherently. I just picked that. I just said,
Did you
let's
pick
do
it
this order.
intentionally?
What's that?
Because did you pick it intentionally because it makes it easier? Or
Well, doing DZ first is just easy. So if we want to do type A2, that's a little bit. There's a little bit more to it, but so type 2 would still be 0 to y squared, but now we're doing. You can write it down. Dx would go from what to what? X equals 0 to.
4 minus x squared.
But now it needs to be x equals. So be
4 minus y squared.
square root of 4 minus y. Because you have to solve this for x. Sorry. Right? So if that's 4 minus y, 4 minus x squared equals y, then x equals square root of 4 minus y. Solving for x. And then y going from 0 to 4. So only slightly harder just because we got that one more step of solving this parabola for x.
So by solving this triple integral, would we find the volume of the solid?
It would find the volume of the solid if what? If this function was what? This is the analogous to what we saw with double integrals. Because the solid is the thing that we're integrating over, right? So the solid now is like what the region was in a double integral. So what's that?
So would it work if the function is always positive for that domain?
Okay, but so
Must always equal 1.
yeah, so what this, so if this is some function of x, y, and z, right? So this is a function of x, y, and z, then what does this compute? It computes the difference of four-dimensional volumes, right? So whatever sometimes they call those hypervolumes, right? Like this volume that's, we can't really imagine it too well. It's hard to illustrate because it's four-dimensional, and it would be the difference because this function could be negative sometimes and positive sometimes. But like with double integrals, we said we could trick it to giving us the area of the region by doing what? Integrating
An f of 1.
1, right? If f was 1, then it'd be like a volume with height of 1, and so the volume would equal the area of the base. And so we kind of trick it and trick the double integral into finding area for us by finding an equivalent volume to the area. So now we're stepping it, so now that whole conversation is the same, but stepped up one dimension. So now we can trick this triple integral into finding volume in R3 for us by doing what?
Setting f equal to 1?
Right, so if we set f equal to 1, then it finds this hypervolume, but that value of that four-dimensional volume is the same now as the value of the three-dimensional solid volume that is like the limits. Just like this could find area by using f equals 1, now this could find volume by using f equals 1. Okay, does that make sense?
Mostly. I guess my biggest issue is just trying to understand and visualize what this information actually means. But since it's in 4 dimensions, that's not really...
Yeah, you're not required to do that. You just know that this is a four-dimensional function that we're integrating over a three-dimensional solid, meaning we're integrating all the points, we're integrating that function for all the ordered triples in our solid. And that will give a difference, a net volume, but four-dimensional volume.
Okay.
If you make the function 1, then that four-dimensional volume that you get will have the same value as the three-dimensional volume of the solid, which is the same analogous situation to making the function 1 in a double integral and getting the area of the region. Okay, but we got to move on.
I know. Okay, thank you.
Yeah. Okay, let's look at one more of these. Let's look at B. So let's do B2. So B2 would be dx and then dy dz. Okay, so dx means what's our surface to surface?
Left to right.
Left to right. Dx is left to right.
Or back to front.
Back to
sorry.
front. Back to front. The back is x equals 0. The front is, so all the arrows are going to exit out this vertical surface.
X squared.
So that's going to be, and we need x equals, so it's going to be the square root of 4 minus y, again. So it needs to be x equals, right? X equals. And then we're going to do the projection into the yz plane. Which looks like this. Oops. So here's y, here's z. Okay, and then this is 4, we know. And this is 4/16. All right, so now we're going to go left to right. So in the double integral, so the left side is what? What's the left?
Square root of z.
Good. Y equals, it's going to be square root of z. Good. And then the right is 4.
4.
And the bottom to the top, the bottommost one of those is at z equals?
0.
Up to the topmost one is at?
4.
4.
Nope. Z equals?
16.
16.
Oh.
So there's B2. Okay, questions on these examples? Okay, so just while I'm thinking about it, today's quiz is longer and it's not during class. It is already open. Once you start it, though, you don't get a second chance, but you get as long as you want. Okay, so you can take as long as you want on it, but just make sure you're ready when you start it, because you can't. Once you start it, that's it.
Is it on our own time like the other one was?
Yep. So it just has to be done by midnight tonight. So anytime this afternoon or tonight, just do it by midnight. It is definitely based on today's class, very, very closely related to today's class. But you want to have a little less pressure with time and be able to think and work it out. So that's today's quiz. So we'll have till another 15 minutes to do examples here. Can I go on to the next one? Any questions on the A1 or the B2? Okay, new example. Just before we do the last example, let me show you in WebWork on number 1. So it has to be at least a little bit of ability here to sketch surfaces and come up with the solids. I think problem 1 is a good one to talk about and practice together here. So your numbers might be a little different, but it's going to be the same general idea. So my solid is bounded by z equals 0, x equals 0, this plane, and y equals 8. Okay, so y equals 8. I'll just draw that, kind of sketch that first. Looks something like this. Right, so that's a vertical plane through y equals 8. Z equals 0 is the floor here. X equals 0 is, again, the back. That's like the plane of the screen. So this last one is z equals 4, y equals 4, minus 4x. So there's different ways to sketch this, but one way that works for sketching a plane like this, it's not entirely obvious what it looks like. Set one of your variables equal to 0. So for instance, I could set x equal to 0. And when I do that, I'm going to get the intersection of this plane with the yz plane, where x equals 0. So what is that? That's going to be z equals y. So x equals 0 is the plane of the screen. That's the yz plane. And in that plane, this plane intersects it at z equals y. It's like this. So we should extend y equals 8 plane up a little bit. So it goes right through that point in the plane y equals 8, and then it comes through the other side. Okay, likewise, I could do y equals 0. and I get the line z equals, oh, did I do this wrong? Wait a sec. Y equals 0 is z equals negative 4x? And maybe I did z equals 0. Yeah, I did z equals 0. Sorry. Okay, that's right. So z equals 0, I want to do z equals 0. That's easier. So z equals 0 is y equals 4x. There we go. That's what it was. All right. So here's z equals y in the x equals 0 plane, and then y equals 4x is going to be like this. So it's going to intersect the plane right there. And so then you can see the plane forming here, right? So that these two lines, the z equals y in the x equals 0 plane and y equals 4x in the z equals 0 plane, are both lines in the plane. So they form the plane. So you can kind of see this plane. Well, it's kind of leaning back this way, but then coming out at us also. So if we have the x equals 0 back there and z equals 0 and y equals 8 and this plane, then you can kind of see this thing taking shape like this. So that's a little hard, trickier one to do, so I wanted to help you with that. But does it make sense, kind of the strategy here?
So what is the plane that's... I'm not really sure how to... So not the one with the 8, but the one in between the 8 and the y. That's plane that you drew.
This triangle here?
Not that triangle.
This one here?
Yeah, that.
That's just y equals 8. That's just vertical plane coming straight out at you, out of your screen. It's
So
parallel to the x, that's y equals 8. It's parallel to the x-axis. And it's vertical. It's this right here.
So
It's this right here.
Oh, so that smaller triangle is within that larger plane?
Yeah, that's the y. This is the y equals 8 side of our solid. Y equals 8 right there.
Oh, okay, because it kind of looks like it's like moved farther inside than that larger plane. I think it's just a matter of perspective.
Yeah.
That's my issue.
Let's see. Does that help? Does that help now?
Yeah, thank you.
Yeah, sure. Okay, so that's that one. So I think the other ones are a little bit more manageable, and so you really want to practice without technology, sketching these surfaces. See if you can do this. See if you can make the solids a sketch of the solid good enough to start writing the limits of integration. Okay, but we got to get to the other example here. So I'm going to get to this one. So now what are these? This one's a little easier to draw, I think. What is this right here? Z equals 5 minus y.
Linear cylinder.
And what's that?
Plane.
Yeah, that's a plane. It's not a line. It's based on a line, that we can start drawing that line, but this is a plane in R3. And then what about this?
Circle. A cylinder. A circular cylinder.
It's a cylinder. It's not a circle. It's based on a circle. It's not a circle. It's a circular cylinder. Extending in the x direction. So it's going to be radius 2. Like that. And then z equals 5 minus y. So what is that? We can start with a line in the yz plane. Here's y. Here's z. So the intercept is at 5. and then it has a slope of -1. Like that. Too steep. And then now imagine that then being extended in the x direction. Right? And so that's going to slice through. It's going to, imagine this diagonal line here slicing through that cylinder this way. What's the resulting, what's going to happen when you slice through like that? You're going to get like an ellipse, right? Like, because it's going to be like a circle slanted and stretched in this way. So it's going to be like an ellipse. So maybe a better drawing for this will be this. So here's a, so this is what we got. The bottom is equal 0. The top is this plane. And then the lateral sides are defined by the circular cylinder x squared plus y squared equals 4. Does that make sense? Got to move here. Oh no, don't do that. All right, so something like that. So let's do, we're going to start with B. B2. B2 is dx, dy, dz. So we start with what surface to what surface?
Back to front.
Back to front. What's the back of this thing? X equals what?
4 square root of 4 minus y squared.
Good. So so the back of it is going to be the negative x values on this on this cylinder, the circular cylinder back there. So we got to solve this for x, which means x is going to equal plus or minus square root of 4 minus y squared. So the back is going to be the negative, right? Back there in negative x territory. The back half is negative 4 minus y squared. And the front is?
Positive.
Positive version. Okay, and then dy dz. Okay, so now we need to project this thing into the yz plane. What will that look like? Can you imagine if I take this thing and flatten it on the yz plane? Right, because it's going to right.
A right trapezoid.
Okay, good. So if we're looking this way at it, all the circles are going to disappear. We won't see anything curved anymore. Does that make sense? All we're going to see is straight line edges here. And then we're going to see this straight line top here. Like that. We won't see the circles that are in the x direction, right? The circles kind of. So that's what we'll see. So if we're going to do, what are we going to do? We're going to do dx, dy, dz. So y is left to right. And so first, so for this region, we're asking now, what's the left side and what's the right side? So what's the left side of this region?
-2.
Yeah, -2. That's right. Left side is y equals -2. What's the right side?
We have to split it up into 2 parts.
Okay, someone's saying we have to split it up. The right side, agree?
Yes.
Yep, for these high z values up here, the arrows exit out the, the slanted line. For these low z values down here, the arrows exit out the vertical line. So this is what? Y equals, so this is z equals 5 minus y, which is the same as y equals 5 minus z. So -2, it's the left side's -2, the right side, the first right side is 5 minus z. Okay. So then we said what, the left side's always -2. So what's the other right side? So we got part of the right side is 5 minus z. The other right side is 2. So when is the right side 5 minus z? So this is our 5 here. And by the time you make it out to 2, we're down to 3. If you go back to -2, we're up at 7. So for what z values is the right side 5 minus z? From?
3 to 7.
3 to 7. And for what z values is the right side 2?
0 to 3.
That's it. Got it. Okay, questions on that? Okay, so I've got another example. It takes about 10 minutes. So if you need to leave, it will be on the video. But for those who can stick around, I'll work it through. But it's an important example. It's a little bit tougher. And if you can do that one, then you're in good shape for what you need to do. So feel free to just take off when you need to. Again, don't forget your quiz. It's due at midnight. Once you start, you have unlimited time, but you only have one attempt. And it's very closely related to today's lecture, okay? So here we go. So I want to do C1. So remember what C is. C is dy first. So that's which surface to which surface? We'll do C1, which is dy, then dz, dx.
Is the left surface to the right surface?
He wants left to right. dy is left to right. Agree with that?
Yeah.
Good. Okay, yep. So it's left to right. So here we go. So what's the left side of this thing?
Negative square root of 4 minus x squared.
Good, right? So it's solving, so it's this parabolic, it's the circular cylinder solved for y. And so that is y equals square root of 4 minus x squared, actually plus or minus. So the left side is going to be
The
negative, right? The negative square root. Okay, and what's the right side of this thing? Where did our arrows are going to enter in over there, and they're going to exit where?
2, so we would have to split it.
Some of those arrows are going to exit out this plane at the kind of the topish point. Some of those arrows on the right are going to exit out the circular cylinder. So let's do the. So we're going to have to add. We're going to do sum up. So the left side is always negative radical. Sometimes the right side is positive. Sometimes the right side is, what's the other choice? Y equals what?
5 minus z.
5 minus z, the plane. Right, this plane is z equals 5 minus y, or y equals 5 minus z. Okay, now we need the projection into which plane? Projection into
Zx.
xz plane. So what will this thing look like in the xz plane when we project it? Meaning we're going to flatten it. So it's like we're just going to flatten this solid, like clap our hands and just flatten.
It's just gonna be a rectangle, isn't it?
Okay, so the bottom is like a rectangle, that's true. The top isn't quite a rectangle. The bottom is rectangular until we get up to, so this was level, this was 3, this is 5, and this is 7. So what's going, starting at 3, what are we going to see in the projection?
A circle.
Yeah, so what we're going to see is,
So a circle with the radius of 2.
yeah, a circle with a radius of 2. So if we flatten that ellipse onto the xz plane, it's going to actually flatten as a circle. And that's, the whole circle is going to be important because the top half of the circle is like the top of this thing. But the bottom half is super important because it's the dividing line between what? Between this surface and the front lateral surface, which is our breaking point. So it's not, so you may think you're just drawing this. But this, make this taller. So it's more than just like that shape right there. You also need to have this as part of it because that is truly the dividing line between the right side being this front surface and the right side being the flat surface. Does it make sense? So this is a little more complicated because this boundary right here, we need to write that in terms of x and z. And so that's the intersection of these two, neither of which are x and z. So we need to combine these equations to get one equation of x and z, and that will be this circle right here. Or we can just see what that, we know that's a circle. This is 3, this is 5, this is 7. We could just write the equation of that circle based on our picture. What's the equation of that circle? Center is at?
X squared.
0, 5. Radius is?
2.
2. Just remember it's x and z, not x and y. So it's going to be?
X squared minus, or x squared plus z minus 5 squared is equal to 4.
That's it. Right, center 0, 5, radius 2, but just remember this is the xz plane, not the xy plane. And this is the equation you will get if you combine these two equations. Okay, so if you combine these two equations, if you solve this for y, plug in for y and get x and z, you get the same circle. And so, but we need what we're doing dy, dz, dx. So we're going to need this thing solved for z. Well, let's get there when we get there. Okay, so we know that the left surface is the negative radical 4 minus x squared. The front surface is, sorry, the right surface is split up. So for what projection, what part of this projection is the front surface the negative 4 minus x squared?
The bottom half.
Good. Yeah, it's going to be this bottom part down here, right? This is the front, this is the right side of the circular cylinder. So this is going to be this integral down here. It's It's going to be based on this region here. So dz is bottom to top, so z goes from what to what?
0 to 3
Not 3.
to 5. Wait.
Not 5.
0 to
Oh, to
the equation.
This, right?
Solve for z.
0 to this, the bottom half of the circle. So we got to solve this for z.
Yeah.
So we're going to have 4 minus x squared. We're going to have square root, plus or minus, and then we're going to add 5. Okay, so so what is the bottom, right? So the bottom is 0, and so the top, what is the bottom of this circle?
So the negative.
So the negative. So it's going to be negative square root of 4 minus x squared plus 5. Okay, and then that from what to what? So from 0 to the bottom, from
Negative 2 to 2.
-2 to 2. Okay, that's when the right side is the circular cylinder, 4 minus x squared. Now, what about when the right side is the plane, 5 minus z? Z goes from, that's going to be, here's the plane, right? Here's the projection of the plane. It's the circle, the disk. So z is going to go from bottom to top, which is z equals,
Negative square root 1.
right? This thing again is going to go here,
And then it's going to go to the positive.
positive. And that from,
Negative 2 to 2.
again, -2 to 2 again. Did I lose you? So that we just finished that one now. So the right side is split up, and this bottom portion here is when the right side is the circular cylinder, 4 minus x squared. So we go from 0 up to the bottom of the circle. And then also the right side is this plane, which is this disk here. And so then z goes from the bottom of that circle to the top of that circle. And then both of those from -2 to 2.